Hey there, and welcome. Today, we're diving into the absolute foundation of, well, everything. We're not just talking about physics. We're talking about the fundamental language that scientists use to describe reality itself. It's kind of like the secret code behind a boiling pot of water, all the way up to the expansion of the entire universe. So let me start by asking you something that sounds, well, kind of impossible. How can this vast, complex, and seemingly infinite universe be understood and described using just 7 core ideas? Sounds nuts, right? But stick with me, and by the end of this, you'll see exactly how it's done. All right, so to get this language, we gotta start with the basics. I'm talking about its alphabet. These are the absolute most basic building blocks, the letters that physicists use to write every single concept. See, before we can even begin to describe something, we have to agree on what we're measuring. That's a physical quantity. It's basically any property you can slap a number on. The length of a table, the mass of a planet, the temperature outside. It's the what in all our scientific sentences. Okay, and this is where it gets really cool. We have what are called fundamental quantities. The best way to think about them is like the primary colors of our universe. They're the absolute originals. You can't get blue by mixing other colors, right? Same idea. You can't create these quantities by mixing anything else. They just are. And here they are, the whole shebang, the entire alphabet of reality. You've got length, mass, and time. Those are the big 3 you probably know. Then there's electric current, temperature, the amount of a substance, and luminous intensity. Every single physical idea, no matter how complex, is built from some combination of these 7. That's literally it. Okay, so we've got our letters. What's next? Well, you start putting them together to make words. And that's exactly what physicists do. They combine these fundamental quantities to build more complex concepts. And the difference here is it's super simple but really powerful. On one side, you've got the fundamental stuff, the absolute building blocks like mass and length. And on the other, you have everything we build with them, the derived quantities. One can't be broken down any further, the other is just a mix and match of the basics. The big takeaway here is that a derived quantity is always dependent on the fundamental ones. You see, you can't have something like speed if you don't first have a concept of distance and time. You can't talk about density without first understanding mass and volume. They are all derived from that original 7-letter alphabet. Let's actually build one right now. It's super easy. So step 1, we grab a fundamental quantity, length. Step 2, we grab another one, time. We divide the length by the time, and boom. Just like that, we've constructed a brand new concept, velocity. And you can see how this just keeps going, right? It's amazing. We can combine mass and volume to get density. We can take that velocity we just made, combine it with time again, and now we have acceleration. From there, we can build force, and from force, we can build pressure. It's like this beautiful cascade of creation, and it all starts from just those 7 points. Okay, so we've got letters, we've got words, that's great, but any language needs rules, right? A grammar. Otherwise, it's just chaos. To communicate, everyone needs to agree on what the words actually mean. We need a universal rulebook. And in physics, that rule is called a unit. A unit is just the agreed-upon standard that gives our measurements meaning. I mean, if I told you a stick was 10 long, what does that even mean? Nothing, right? But if I say it's 10 times meters long, now you know exactly what I'm talking about, because we've all agreed on what 1 meter is. You know, it wasn't always this straightforward. For a long time, things were kinda messy. Different places used different systems. You had the FPS system with its feet and pounds, the CGS system with centimeters and grams. For science to really work on a global scale, everyone needed to get on the same page. And thankfully, that's exactly what happened. The world of science settled on the International System of Units, or as it's better known, the SI system. This is the universal rulebook. It's what makes sure that when a scientist in Tokyo measures a kilogram, it's the exact same kilogram a scientist in Buenos Aires is measuring. It's the absolute foundation of global science. Okay, so we have our letters, our words, and our grammar. Now for the really, really cool part. Mastering this language gives you a kind of superpower. A tool so powerful it lets you check your work and even discover new relationships in physics. This superpower has a name, dimensional analysis. And it's basically the ultimate grammar checker for the universe. It's a way of looking at how different physical quantities are related, just by breaking them down into their fundamental building blocks, their dimensions. Whoa, okay, this table might look a little intimidating at first, but trust me, the idea is actually super simple. We can represent any quantity using symbols for its fundamental parts: L for length, M for mass, T for time, and so on. So, for example, look at area. What is it? It's just length times length. So its dimensional formula is just L squared. Or velocity. We know that's length divided by time, so its formula is L t to the minus 1. See? Every single concept has its own unique dimensional signature.
So what can you do with this superpower? Well, for one, you can easily convert units from one system to another. Two, and this one is a game changer, you can check if an equation is even possible. If the dimensions on one side of the equal sign don't match the other side, then your equation is just plain wrong, period. And three, you can actually figure out the basic form of an equation just by looking at the dimensions involved. It's an unbelievably powerful tool.
So let's bring it all home. We've gone from 7 simple letters all the way to a system that can verify complex equations. So why does any of this matter? What's the big picture here? Well, it really all boils down to this one incredible idea. The entire mind-boggling story of our physical world, from the tiniest atom to the biggest galaxy, is written in a language that has just 7 letters. What that means is that underneath all the chaos and complexity we see, the universe has an elegant, coherent, and ultimately an understandable structure. It's honestly one of the greatest achievements in all of science. But, it makes you wonder. As we push the boundaries of what we know, as we dive into the really strange worlds of quantum gravity and dark energy, what might the next universal language of science look like? What new fundamental letters are still out there, just waiting for us to find them?